With this diagram, we will give the introduction. This is the VI characteristics. How it is working here is, first, as we are applying PN junction diode in forward bias, first the current is increasing. Next, the current is decreasing. Again, the current is increasing. Why this is happening means this is based on Fermi levels and valency and conduction band. We will see the diagrams, how it is working. Here we have this is conduction band. Down part we have valence. ఈ రోజే బోర్డు తెచ్చుకున్నాను సార్, ఎలక్ట్రిక్ బోర్డు కొంచెం సెట్ తెలియట్లేదు. హియర్ we have Fermi energy level EV.
मैडम नोट विजुअल मैडम नहीं दिख रहा है।
కనిపిస్తుందా అమ్మా ఇప్పుడు? Can you see now? Here this is the PN junction diode. अब दिख रहा है अब?
यस मैडम।
Okay. This is the which you have this diagram in the material, how actually the current is increasing. In this diagram, I'm saying that current is increasing. So this is the VI characteristics of tunnel diode. First, the current is increasing. From 0 to the tip point up to 2, the current is increasing. From the point 2 to 3, the current is decreasing. Again, the current is increasing. How it is happens is based on this diagram. Now we will see how this current is increasing and decreasing. Here, the current increasing and decreasing is based on PN junction diode. First, I am not applying any supply. Can you observe this diagram? What is EC in this diagram? EC is conduction band, energy level of the conduction band. EV is the energy level of valency band. For the P-type material, we have Fermi level below the valency band. EF. What is EF? Energy of the Fermi level. This energy of the Fermi level is below the valency band for the P-type material. For the N-type material, this Fermi level is above the conduction band. First, I am not applying any supply voltage in this diagram. Without applying supply voltage, there is a tunneling phenomena. Tunneling phenomena means whatever the holes we have in valency band, it will transmit to the conduction band. Whatever the electrons in the conduction band, it will transmit to the valency band. This is without supplying of energy. Now I am supplying a little bit of energy. If I am supplying little bit of energy, what happens? This whatever the electrons we have in conduction band, that one is moved to the valency band. Movement of electrons will take place from the conduction band to the valence band. So here just observe the level of Fermi here. Without applying supply, we have across the conduction band some empty states as well as we have some empty states as well as filled states. Here in the conduction band, in the beginning we have empty state. After that we have filled state. Whereas in the second case, this when we are supplying voltage, the conduction band is completely filled. If this is completely filled, the tunneling phenomena is taking place. What is the phenomena of tunneling? Here in the N-type material, we have electrons. In the P-type material, we have holes. This N-type material, electrons is moving towards the P-type semiconductor material. This is happening for the voltage up to 5 volts. Next, if I am exceeding my voltage, if the voltage is greater than 5 volts in this region, here this second part from 2 to 3. So from 0 to 2, what happening? The current is increasing. The current is increasing means whatever the 4 electrons we have in N band, that is moving to P side. From 2 to 3, the current is decreasing. What is the reason for decreasing of current? The decrease of current reason is here, the difference here, the Fermi level for the P type we have this side, for N type we have this one. So here, the compared to the previous one, for up to applying 5 volts, this conduction band is filled. Whereas for if I am increasing above 5 voltage, the Fermi level is going towards the upside. So there is a very difficult for funneling phenomena. So it here a gap is displayed. The same thing now I will show on the whiteboard. What is the graph we have? VI characteristics of the graph. First phase is current is increasing. Next phase current is decreasing. Next phase what happening? Current is increasing. Here this point I am calling as a peak point. My current is IP. Maximum current is flowing here. Next here this point I am whatever the maximum current is flowing, that point I am calling as VP, peak valley point. Next again here the current is decreasing. This point I am calling as VB. Again here the current is decreasing. Based on this diagram, how energy level diagram is working. Here we have conduction band.
Excuse me, ma'am.
Cheppandamma.
Sorry to disturb you, ma'am. Could you please take a black color one because it is not like
Okay.
visible, ma'am. Yellow one.
Okay, okay. Is this okay now?
Yes, madam.
Okay, so. First, now we are seeing the VI characteristics. This is very important question for semester, for theory examination. Initially, the current is increasing. Up to peak point, the current is increasing. This peak point, whatever the current here is, this I am calling this as peak current IP, and the position of the voltage I am calling as VP. Again, the current is decreasing. Up to some extent of the point, current is decreasing. This point I am calling as a valley point VB. Again, the current is increasing. So this increasing of current, decreasing of current, increase of current. These three is basing on the Fermi energy levels. Now we will see the Fermi energy levels for the corresponding diagrams, how this Fermi energy level is working. In the beginning, I have here the energy of valency band. Next here, I have energy of conduction band. These diagrams you can observe in your textbook, page number 76. Here we have conduction band and valency band. For the p-type material, we have Fermi energy level below the valency band. We have Fermi energy level below the valency. First, I am drawing diagram 8.1 figure A from the textbook. Here we have valency band, conduction band, and Fermi level. Which diagram I am taking? I am writing diagram for p-type material. Which material I am drawing? I am drawing diagram for p-type material. For this p-type material, the Fermi energy level is below the valency band. This side I am taking P. Same way I am taking other side is called as for N-type material. Here N-type material, again I have conduction band. Again here I have conduction band, valency band. But the Fermi level for the conduction band is above. But the Fermi level for the N-type material is above. Again I will write here conduction band, valency band. Where is the Fermi level for the p-type material? Here the Fermi level is below the valency band. This is for the which one we are taking? P-type material. The same thing I am writing for the N-type material. For the N-type material, wherever I have Fermi level, the same corresponding point I have Fermi level. Where is the conduction point? The conduction band is across EV. Here I have conduction band EC. The Fermi level is here. Then where is valency energy? EV. See, these diagrams is in the textbook. The difference between these two calling as a potential barrier. This one part is P-type, other part is N-type. This valency band from here to here, this conduction band from here to here. This is the first diagram from the textbook. This from to here, this point. But For the p-type material as well as for the n-type material, the Fermi level energy is across the same position. So here this p-type material we are having holes. For the n-type material, we have having electrons. So both are in the same region or maintaining on the same. So tunneling phenomena is taking place. This from is moving to here. This is moving to here. This is the first figure 8.1 A diagram. So this is possible before applying energy. This diagram is belong to before applying energy. Again, in the textbook, we have second diagram. What is the second diagram? Same type of diagram we have when I am applying reverse bias voltage. Figure B is reverse bias voltage. In the reverse bias voltage, we have conduction band EC and I have valency band EV with the Fermi energy level EF. This is this side. This is for p-type material I drawn. Same thing now you draw for n-type material. For n-type material, wherever we have EF, Fermi energy level, like this we have Fermi energy level. This side, the Fermi energy level is started here. Means wherever this starting point to here, this is here starting point, this is ending. This Fermi energy level for so what happening in reverse bias condition? Tunneling phenomena is occurred, but here the particles is moving from p-type to n-type material. Next condition, third condition we have when we are applying 5 volts supply. First condition is no supply energy is applied. If no supply energy is applied, easily can move from one place to another place. From p-type to n-type is shifting, from n-type to p-type to shifting. This case is for which one? Without energy applying supply energy. Second case is reverse bias condition. In reverse bias condition, moving of electrons from one place to another place is occurred. From where to where? From p-type to n-type. Next, from third case. Third case is what? I am applying plus 5 volt voltage. If some forward bias voltage I applied, what happening? From current is starts flowing, the diode is conducting. If the diode is conducting, the tunneling phenomena is taking from where? From N to P. This is shown in the first graph. What is our first graph? Here is here first graph. I drawn one first graph. What is this first graph? From here to here, current is flowing. At this point, current is flowing means the particles is moving from where to where? The particles is moving from N to P. Actually, this is forward bias diagram. If I'm taking the same reverse bias diagram, the particles is moving from where to where? P to N. This is case 2 in second figure in the textbook. This is third figure in the textbook. What is the first figure in the textbook? When there is no power supplied. If there is no power supply condition, what happens? Tunneling phenomena is taking place from P to N easily. If both having same level of EF. If both having same level of EF, P2 is N shifting, N2P is shifting easily. This is case 1 diagram from the textbook. Energy level diagram. This is the first energy level diagram. EF of both P-type and N-type are at the same level. Easy to shift from P to N, N to N. This is the first case. What is the second case textbook diagram? Second case B diagram is when we are applying some reverse voltage. If we are applying reverse voltage, what happening? I will show here. In the same waveform, reverse bias. This case is forward bias diagram. This case is reverse bias diagram. Even in the reverse bias, because of reverse minority charge carriers, more current is flowing. Actually, reverse bias diode is not conducting. But here I am saying this current is flowing more. This more current is flowing because of reverse bias current. In reverse bias current, what happening? The electron hole movement is taking place from P to N. This is completely reverse bias case. Next, forward bias case. In forward bias case, the movement of electrons is taking from N to P. In textbook diagram, this is third diagram. This is second diagram. In this graph, first graph is not shown. What is the first graph? Without applying any energy, easily movement of electrons and holes is taking place. This is the first case. Next, in this diagram, now, up to which part we completed? third case, current is flowing. Up to which extent current will flow? Up to the peak point V, up to the current, maximum current IP across VP, the current is flowing. Up to this point is okay. Next in the figure, we have C on the textbook. C and D is related to up to this diagram. Page number 76. Don't get confusion because these diagrams are very smaller in textbook. First diagram, what first diagram represents? First diagram represents we are not applying any power supply voltage. Next, we have B diagram with applied reverse voltage. If I am applying reverse voltage, what happening? Here we have Fermi level EF for the P type. Whereas for the N type, what happening? We are happening N type Fermi level is here. So this is a little bit up, this is a little bit down. So it is flowing from where to where for reverse bias condition, it is flowing from P to N. Next, third case. Third case is from here to here. In third case, what happening? Current is starts flowing. In this case, tunneling movement is from where to where? From N to P. The energy level diagram, how EF is represented in this? Suppose if you have EF here, the next EF is a little bit like this. You just observe where is your Fermi level in the diagram. While studying, you observe where is your Fermi level in the diagram. Next, we have another diagram called E diagram. What is E diagram and F diagram? E and F diagram represents if we are applying more voltage, up to some peak point voltage is applied. Up to this point, suppose I imagine that my voltage is 4 volts. Suppose I'm going beyond 4 volts to 10 volts. If I'm increasing voltage, what happening? If I'm increasing voltage, this is axis VI characteristics. Here we have V, here we have I. If I'm beyond from, imagine, suppose I'm increasing from 4 to 10, this is decreasing. Why it is decreasing and again why it is increasing. This decreasing part is represented with figure number E in your textbook, 8.1 figure E, because you also written assignment, same topic. Figure number E represents 8.1, figure E represents this part. Next, up to this point is reached, this is the diagram F. Next, this is increasing. Now we will see that why this is decreasing, why this is increasing. This decreasing and increasing part, you can refer your figure numbers 8.1 E and F. In what we have figure number E and F diagram, same again we will draw. What we have diagram? Here I have conduction band EC. Next, here I have valence band EV. Next, what happening? Here, where is we have Fermi level for the P-type material? Fermi level is across the down part. This is for which one? This diagram I wrote for P-type. This diagram I wrote for P-type. Same diagram, now we will see for the N-type material. Here, N-type material, somewhere down part, where we have, you just, these diagrams are very important. Here, between EV and EF, my conduction band is started. Between EV and EF, conduction band is started. Above EV, I have Fermi level. Above EV, I have Fermi level. So, is it possible this position to this position tunneling? The position of Fermi level gap is more here. This potential barrier gap is more. So, no tunneling phenomena is taking place. Moving of electrons from one place to another place is not possible. Previous cases, we have Fermi energy level here, and for the P-type, for the N-type, Fermi level is easy here. So, easily movement of holes and electrons is taking place before applying energy. When I applied forward bias 5 volts, what happening? We have EV here, some EF here, somewhat a little bit position we have EF. Here, at least jumping is possible. Tunneling phenomena means cross moving of electron and holes place is taking place here. But whereas in third case, what happening? Here we have EF. Here we have here. Means the position is changed as we are applying more voltage. So here, no, it is not possible to transmit, jump from here to here, here to here. For that, the current is decreasing. Which part current is decreasing here? From this part, current is decreasing. So you can observe figure number E and F. Figure number, what is the difference between figure number E and F? In figure E and F, we have small, I will show the same diagrams in the PPT, which is more clear for you. Now, whatever I explained, The same diagrams here. Now, what is the first diagram? What is the second diagram? What is the third diagram? What is the fourth diagram? In the first diagram, before applying potential energy, just observe both EV. EV is valency energy level. Here you have EV valency energy level. If Fermi energy level and Fermi energy level is more near, so the thermal transmission of electrons and holes taking place. This voltage is between 0 to Vp. Next, what is the second diagram? Up to peak point Vp, maximum current. At that time, all filled. This is empty states. This is called as filled states. So, a maximum filled states of the conduction band up to Vp, peak point. Means in the figure number 1, the current is increasing. In figure number 2, the current is increased up to maximum extent. Next, what is the third figure? There is just observe EF. EF is here and EF is here. The position of EF, here we have down part filled states and this crossed lines is empty states. So a little bit gap is increased. This gap is increased means tunneling, jumping of electrons and holes is difficult. This is up to as voltage is increasing, this happens. Again, you will get another doubt. Why this? Then again, why it is increasing? One more doubt is why it is increasing. I said it is decreasing. Is it? First, it is increasing. Forward bias voltage applied increasing. As Fermi energy level gap is more, it is decreasing. Up to this point, it is decreased. Again, I am saying that from this point, again increasing. Then what is the reason for increasing this point? Here, this is forward bias. Up to Vp, it is increasing. As I'm increasing voltage level, it is decreasing because of Fermi energy level position. Unable to jump from one place to another place. Up to this extent is okay. Again, I'm saying that this is increasing. Why this point is increasing? At this position, this tunnel diode is, what is the symbol of tunnel diode? Like this. This tunnel diode is converted into normal diode. This tunnel diode is converted into, as we are increasing more voltage, suppose here the voltage is 10 volts. Beyond the 10 voltage, again it is acting as a normal diode. So this is the topic of tunnel diode, very, very important question. So from the PPT, we will see what is tunnel diode. It is a heavily doped PN junction diode. Here we are applying, before applying field up to 5 volts, the current is increasing. From 5 to 10 volts, the current is decreasing. Beyond 10 volts, again, this tunnel diode acts as a, which diode? Junction diode. And now we will see the points. A tunnel diode is a heavily doped diode. Here we are applying voltage, high voltage we are applying. Which high voltage is applied to the PN junction diode. If I am applying high voltage to the PN junction diode, it acts as a tunnel diode and we are calling it as a tunneling effect. Next, what are the uses we have? We are using this one in high frequency oscillators as well as amplifiers. At low frequency, the charge carriers is moving from one place to another place and tunneling effect is happening. So this graph you have to explain. For this graph, in the textbook, we have 2 pages of matter. Figure 8.1, figure 8.2, figure 8.3. This one you have to elaborate with 4 different types of Fermi energy level diagrams. What is the first figure 8.1a in our textbook? Figure 8.1a in our textbook is I am not applying any energy. Figure 8.1b is I am applying reverse voltage. Next figure 8.1c is suppose if I am applying forward voltage up to Vp. This one. This diagram is in our textbook 8.1c. First diagram in our textbook is 8.1c. Second diagram is 8.1d. Third diagram is 8.1e. Fourth diagram is 8.15. The same thing is represented again with how we are getting energy gap. How much energy gap is there? In general, normal PN junction diode, we have valency band, conduction band. The energy gap is represented with Eg. Suppose if we are applying doping to P-type material, what happened to your energy valency band? Just observe this one. What is the difference between the figure A and figure B? In figure B, we have valency band. Whereas in figure B, the valency band is reduced. So here, this is the difference. If I am applying doping to the N-type material, what happening? The position of conduction bond is changed. Here we have position of conduction bond here, whereas in this case, the position of conduction band is here. So this is the diagram of tunnel diode. Now we will see the derivation part of the tunnel diode, which is explained in the page number 78. Open your page number 78. Now we have derivation part of page number 7. So in the examination, two types of questions is asking about this question. What is the first question they are asking? Explain about the characteristics of tunnel diode. Explain the characteristics of tunnel diode means up to this waveform explanation you have to do. And again, another essay question they are asking in the previous year questions. What they are asking question? Application question they are asking. What is that application question? Tunnel diode as a microwave amplifier. What is tunnel diode as a microwave amplifier means what we have to do? We have one diagram in this. What is this diagram? One resistor is connected to this resistor. Another inductor is connected. This is inductor. To this inductor, one capacitor is connected. To this capacitor, another resistor is connected. This is the diagram of microwave amplifier. This is what is this diagram? This is the diagram of microwave amplifier. To this, I am applying some impedance voltage Z in. What is RS? RS is resistance that is connected in signal resistance. Here, what is another we have? Inductor. Inductor is represented with LS. And what is this one? This is capacitor. This is what resistance connected across the load is represented with minus Rn. This is the equivalent diagram of the tunnel diode. Using this, we are calculating gain. What is the formula of gain? G equal to dou I by dou V. Dou I by dou V with of Vn. What is I and V here? I is current, V is voltage. What is G? Here we are, G is calling as negative conductance. This tunnel diode works in negative resistance region. How we are calling, why we are calling this tunnel diode working in negative resistance region means this is decreasing. As current is decreasing, we are calling this part from VP to VV, valley point VV. This VP to VV, I am calling as the negative resistance region. As this tunnel diode works in negative resistance region, I am calculating its conductance, negative conductance. As it is negative conductance, I am representing with minus G. Minus G equal, what is the formula? Dou of I by dou of V. I is current, V is the voltage. With respect to voltage across N. Voltage across N, where N is the negative resistance. So I am writing conductance formula you have to write. Next, what you have to calculate in this? Using this diagram, we have to calculate impedance. Using this, we have to calculate impedance. Now, in the textbook, we have the derivation of impedance. Z in is given. Z in is equals to, the resistance is Rs plus inductor, what we have? J omega Ls. This is inductance point. These two are in series connection and one capacitor and other resistor are in a parallel connection. Resistor and parallel connection. Using these, we are deriving frequency as well as power. Using this derivation part, I am calculating frequency. Here, what is the first term? Series term, I have Rs plus J omega Ls and I have another parallel term. What is parallel term? We are connecting one resistor Rn and what is the capacitor I am using? J by omega C. One term. These two from where I am getting Rn here? From this diagram. This is Rn. What are the capacitor value have? J by omega C. This capacitor value I am writing as J by omega C. Here series term I am taking as Rs plus Ls. In the derivation part, which is the page number 78. This is another essay question. They are asking two essay questions. First essay question is VI characteristics. Second essay question is microwave amplifier application. How tunnel diode we are using in microwave amplifier. Here using this series connection, I am writing one expression Rs plus Ls. Using parallel connection, I am writing as capacitor C. C is represented by J by omega C. And another term we have Rn. These parallel connection, by writing series and parallel, I am calculating the value of frequency. Here, what is the value of frequency from this derivation? the value of frequency we are getting from this derivation is F. Here frequency is represented with F. F of R equal to 1 by 2 pi Rn of C. What is Rn? The resistor across connected load. C is the capacitor times of under root of, we have formula Rn square times of C. Rn square times of C by Ls minus 1. This is the formula of frequency we are calculating. Again, this tunnel diode first diagram. Here we are just checking the variations in this diagram. What is the difference between this diagram and the previous one, which this diagram? Yeah, next here we have two separate subheadings, parallel loading and series loading. What is the difference with the parallel loading and series loading? To this, I'm introducing one load resistor. This is signal resistor RS. I'm including one more load resistor. This load resistor, I'm connecting RL across series. Another one is I'm connecting across parallel. Now we will see the parallel connection. What you have parallel connection? This here, the same resistor you have with some signal. This signal to this signal, I am connecting one load resistor RL. From this, I am connecting one capacitor C. To this, I am connecting one what? Resistor RN. This is common connection. In the previous diagram also, we have capacitor and resistor. But here, whatever the resistor here, I am using this one is called as generator resistor RG. This is the capacitor. Here, I am connecting one extra resistor RL. This RL resistor, I am connecting in parallel combination. One more diagram we have. Same this RL resistor, we have to connect in series combination. How the diagram differs? Same RG we have with signal source. This signal source here I am connecting RL. With what? Next I am taking capacitor. Next I am taking what? I am taking RN. So in the textbook you have two subheadings. One is connecting RL parallel, connecting RL series. By connecting RL parallel and by connecting RL series, we are writing two small derivation part. By connecting load resistor RL in parallel, I am writing power formula. Power P formula, we have P equal to VI, or also we can write as V by RL. Here power from the parallel, I am writing P equal to voltage V square by load resistor RL. Power V square by load resistor RL. Whatever I am writing, this is I am calling this as output power. Same thing we can take here, input power. Power of input is equal to what we have? V square by A times of RL. This is input power, this is output power. Then what is here A? A is called as a gain. These two are the formulas, power of output power and power of input power. Using this output power, input power, I am writing the expression of Pn. Pn is equal to input power plus output power. Input power is how much? V square by ARL is your input power. What is your output power? V square by RL. So this derivation is belongs to which one? This derivation is belongs to parallel loading. This derivation is belong to parallel loading. Next, same way, similar we have CA. Similarly, we have serial loading diagram. Serial loading diagram and serial loading derivation. What is serial loading diagram? Same, just now we written. This is signal resistor RG. Here we have supply voltage. From here we have what we have to take? Serial resistor RL I have to connect in series. From here what I have to take? One capacitor. From this capacitor what I have to connect? I have to connect one resistor RN. Previous diagram, this RL is connected in series, parallel. Here I am connecting RL in series. Using this, we have direct formula is given. We are calculating gain. So what is gain we calculated? RL by RL minus RN. This is the gain formula by making RL common 1 by 1 minus RN by RL. 1 minus RL by RL. So in the still now, from the beginning of the class, till now, what are the things we discussed? First, one topic is completed. We completed which diode? We completed tunnel diode. In this tunnel diode, what we discussed? A diagram, B diagram. From the textbook, I'm saying, we have 8.1. You will read from the textbook only. So on that basis, I'm explaining here. In the A diagram, what we have without applying energy. A diagram is I am not applied any energy. B diagram is I am applying energy, but I am applying that energy in reverse bias condition. If the diode is in reverse bias condition. Next, we have another diagram, C diagram. What is this C diagram? Here I am applying positive voltage or forward bias condition up to 5 volts. If I applied, what happens? So the figure number C and figure number C represents if I am applying 5 volts, 0 to 5 volts. Next, what is D diagram? What is D diagram? If D diagram is if 5 volts is reached, if 5 volts is reached means if peak point is reached, what happens? That is D diagram. Next, we have another diagram called E diagram. From VP to Y, it is decreasing. That is why it is decreasing is represented in E as well as F diagrams. Just read the matter from the textbook, you will understand. From EF diagram represents why it is decreasing. After decreasing, again it is increasing. Why it is increasing? This tunnel diode is acting as a normal junction diode. This is the VI characteristics. After VI characteristics, what we after VI characteristics, what we saw? We saw the application. What is the application? In this application, we are discussing this capacitor and resistor both are connected in parallel. And here the capacitor is variable capacitor or normal capacitor. Whatever the capacitor we are using in the figure, it is a variable capacitor which varying with time like this. This is the capacitor you have. Actually, the capacitor has to show with this symbol. But in our book, we have only capacitor. This is called as variable capacitor. This is normal capacitor. This I am connecting load resistor either in series connection or the same diagram if I connect load resistor with parallel combination. Two cases we observed. So first topic, tunnel diode is completed. Next topic, whatever we are discussing is impact diode. Next topic is impact diodes. Is this clear? In the first slide, I gave just the introduction of the tunnel diode. In the second figure, how the graph is represented. In the third diagram, is represents the energy levels. These energy levels from the figures, you copy these across the diagrams. Which diagrams? Across C, D, E, F. These are C diagram, D diagram, E diagram, F diagram. In this, next here, how the energy levels is different. The four slides talks about the tunnel diode. Next topic we are discussing is here the same is the figure. What is the difference between these two figures? The first figure represents increasing, decreasing, and increasing. Again, the second one is also increasing, decreasing, increasing. But here I am calculating slope, which we already did in the practicals. Calculating slope by taking 2 points. Across the point A, I am taking one value. Across the point, I am taking another value. Across the point B, whatever the value I am taking, that is VB or VB. Valley voltage we will call, peak voltage VP, and increasing and decreasing. These are the second diagram represents the load line diagram. Next topic is this. What is this figure? This figure is general diagram as well as parallel load diagram. In general diagram, we have RS, LS. To that one, capacitor and resistor is connected. This is tunnel diode combination. Next parallel load is here RS or RL is connected in parallel. Application diagram, this one. Next topic is this one. This is also parallel connection diagram. Next one we will discuss about impact diode. Before discussing impact diode, just I will give a little bit introduction on this right up part. Next. So cleared eraser. Next, we are seeing impact diode. Before discussing impact diode, what is the difference between tunnel diode and impact diode? Here, tunnel diode is used for tunnel diode, also called as avalanche diodes. There we are using for microwave amplifiers applications. Here we will use this for solid state diodes. This impact diode is mostly widely usable in case of solid state diodes, and transistors we are using for microwave applications. The full form of impact diode is impact ionization avalanche transition time. Maximum we will use this for in oscillator applications. It is used for producing carrier signals in microwave transmission systems. What is the term carrier signals? Did you remember carrier signal we discussed in the lab? How carrier signal and what is the message signal, both the signals, how it will be? This is message signal. For the message signal, time period is more. If the time period is more, frequency is lesser. This is the diagram for message signal. Next, another signal we have. What is another signal? We have carrier signal. In this carrier signal, we have waveforms like this. Very near waveform. Time period is less and frequency is more. So, this impact diode is used for producing carrier signals. This impact diode is used for producing carrier signals in microwave transmission. It operates from few gigahertz to few hundred megahertz. Actually it is from megahertz to gigahertz it will work. The full form is, what is the full form of this one? Impact diode. What is the full form of this? Impact diode. Full form is impact ionization avalanche transmission time. TT means transmission time. A means here avalanche. IMP means impact diode. IMP is impact diode. A means avalanche. TT means transmission time. How actually it looks? Here either it is in the combination. Actually, how the diode we have in general diode? General diode, how we have? P-type or N-type. If this P-type, N-type, we have small depletion region between P-type and N-type. Here, but here we have combination of PPN and NPN, which is you just observe the page number 81 or the page number 82 from the textbook here. Here, general PN junction diode, PN, which we have small depletion layer. Page number 82, 83, you can refer, but here we have diode P plus NP, or I'm calling as N plus PN. What is this plus represents? This plus represents heavily doping. This plus represents heavily doping. Here P is heavily doped, here N is heavily doped. Here N, again here is P. This one we can write like this. P, N, here you have P. Here between these two, we have depletion region. Here, one more depletion region. These diagrams I will show here on the PPT. See here. First, what we have P plus. What is P plus represents? Heavily doped P-type material. Next, we have N. Next, we have N plus. Between P plus and we have small depletion region. From N to N plus, we have large depletion region. From this N to N plus large depletion region, I am representing as a drift region. From P to N, we have small depletion region. I am calling this as an avalanche region. Either you can take P plus N, I, N plus. What is P plus? Heavily doped. What is, how actual I we are getting? I here is more width. Here barrier potential is more. This more barrier potential I am representing as a different region. More barrier potential is represented as different. See here, tunnel diode is a negative resistance it works as a negative resistance region analog diode. Here, whereas this is of the P plus N plus we will take, or another option what we will take, N plus P plus. Means any ways we can write here. But 1 plus 1 minus we will use. One more thing is here I will explain on the whiteboard. Now you can observe your diagram page number 81. Now we are discussing which one, impaired diode. Page number 81. How here in our textbook it is given? Here it is given N plus. Means N is heavily doped. Next what is given? P is given. Next what you have? P plus you have. So we have combination of N plus P plus. Between N and P, it is works as a avalanche region. We will call this region this as a avalanche region. This P plus gap is more. This gap I am calling as a ionization region. Actually, we will write N plus P plus only. Between N plus P, avalanche region is produced. In place of P and P plus, which region is produced? Drift region is produced. Drift, D. Here, which region is producing? Avalanche region is producing. In this avalanche region, drift region. In this avalanche region, more electric field is produced. In avalanche region, more electric field is produced. From P to P plus, electric field is decreased. Electric field is decreased. Here electric field is more. Here electric field is less. This one is represented in our textbook, figure number 2 and figure number 3. Field distribution diagram is there in the page number 81. You can observe. What you have field representation diagram? We have field representation diagram. What is field representation diagram? Oh, like this you have. In avalanche region, electric field is more. Again, what happening? From avalanche region to up to some extent, while going to the drift region, electric field is decreased. Again, in the drift region, what happening to the electric field? In the drift region, electric field is constant. So again, it is going to 0. This is the second diagram. What is the first diagram in our textbook? First diagram, we have N plus and P. In this N plus and P, what is forming? Avalanche region is formed. From P to P plus, which region is forming? P to P plus, drift region is forming. In avalanche region, electric field is increased. In avalanche region, electric field is increased. In ionization field, electric field is decreased. If electric field is increasing, electric field is decreased. These two are representing with voltage and current. These two are representing with what? These two are representing with voltage and current. See the figure number C. What is the figure number? Same we have. Third and fourth. As voltage is like this, we have one waveform. Like this, we have one waveform in the textbook. Again, we have another one. What is another diagram? When at this point, what we have? Current. What is this diagram represents? This diagram represents in avalanche region, when voltage is applied, current is 0. When voltage is applied, current is 0. For the positive cycle, current is 0. Even in the positive, even this is plus, here from here to it is decreasing. When voltage is decreasing, current is increasing.
Excuse me, ma'am. Could you please tell me once about avalanche region because I didn't get it.
Oh, okay. Here, this is, I'm explaining as per our textbook concept. Here we have N plus. What we here we have? P. Next here what we have? Here we have P plus. Charge carriers, tunneling effect is possible in this region. What is avalanche region? Moving of one to another is taking place. Here we have N, we have electrons. In the P, what we have? We have holes. Recombining of electrons and holes taking place from N to P. recombination of electrons and holes are taking place from n plus to p. This recombination of electrons and holes is calling as the what term I'm calling? I'm calling the term as avalanche. Recombination of electrons and holes taking place from n plus to p. Whereas recombination is not taking place from p to p plus, because why it is not taking place? Here we have holes. Is it? P means holes. N plus means electrons. Whereas heavily doped, but even we have holes. So here is recombination is possible from p to p plus. Recombination is not possible from p to p plus. So this recombination is not possible. We are treating this region as drift region. Whereas here to here recombination is possible. I am calling this as avalanche region. In avalanche region, voltage is increased. Avalanche region, what happens? Voltage is increased. But voltage is increasing up to this. Even this, what is this maximum point? This is minimum point. Up to this point, no current is flowing. Up to this point, no current is flows. Current is flowing from here to here. In the next slide, it is there. I will show. If recombination of electron and holes taking place, it is avalanche region. If no recombination of electrons and holes taking place means that is drift region. Just observe this point. And from in page number 81, C diagram and D diagram, we just observe. In C diagram, what we have? We have like this. Voltage waveform. What is current waveform? Just observe the current waveform. When the current is maximum, if the voltage is 0 at this point, the current is maximum in this point. In this point, the current is maximum. What I want to say, these two are in out of phase. These two are out of phase. If it is increasing, it is decreasing. These two are in out of phase. We will call this as these two are out of phase, 180 degrees out of phase. Here we have maximum voltage. Here no current. Here voltage is 0. What happening to here? This is current is maximum. And next see here, next one. Again decreasing. Again what happens? Again this point. Again in this point, again current is maximum. Again this point, current is minimum. So while in the examination, what you have to explain? In the examination, you have to explain what is avalanche region, what is drift region. Why current is when voltage is increasing. In avalanche region, recombination of electrons and holes taking place. In drift region, no recombination is taking place. As we are increasing here, what is the status of electric field here? Electric field is more in avalanche region. This is important point. Electric field is more in avalanche region. Electric field is less. Electric field is less, which is represented with B diagram. I wrote somewhere here. This diagram. See this diagram. In avalanche region, electric field is increasing. In drift region, electric field is decreased. Again, it is constant for some extent. Again, it is decreased. These two waveforms explanation you have to write in the exam. This is about impact diode. The same thing, whatever I explained. Now I will show this one in the PPT. See this PPT. Now you will understand the function. In our textbook, P plus, what is there in the textbook? N plus P, P plus. Here what is given? P plus N, N plus. So any combination we can take. The first two combination is avalanche region. The next two combination is drift region. Don't keep the second and third PN. If it is PN, again that is also avalanche region. As both are N terminals, we are calling this as a drift region. For here the explanation is given. See here, in avalanche region, both movement is possible. Electron hole recombination will be taking place. Whereas in drift region, this N is the combination not takes place. This is moving towards this side. Electric field is maximum. Electric field is decreasing. And the electric field is constant. The same explanation, whatever I explained, is written in sentence format. How much voltage and current is, how much degrees phase shift we have? 180 degrees phase shift. If the voltage is maximum, current is minimum. Is explained in this diagram. Next, in the textbook, one more thing I want to say, in the page number 82, you have one diagram and graph. This one. This one you have to write for trap-at diode in the examination. Page number 83, you have trap-at diode. For the trap-at diode and this impact diode, you have same explanation. Here, next one is that. Now this is next. So we completed impact diode. Next, we'll come to the next topic. What is the next topic? Next topic, we have trap-at diode. What is trap-at diode? In our textbook, only we have half paragraph, but that is not sufficient. So in the examination, you have to explain which number, page number 82 matter, from where you have one diagram, graph, and derivation part. Those three things you have to write across the page number 83. You have to write. Where you have to write? You have to write all this information in the trap-at diode. Next topic is this one clear. We will go to the next third topic. What is the third topic? Is trap-at diode. Almost the concept of the trap-at diode and impact diode is same. Just what is the main difference here is, see this trap-at diode. In the trap-at diode, again we have P plus, N plus, and N. Whereas in impact diode, which combination we are taking for the impact diode?
Avalanche and madam. P plus N plus combination.
Very good. Now I am giving the difference between two diodes. As per the textbook, in impact diode, the combination is N plus. What is the combination? N plus P.
N plus P.
P plus. Across N plus P, what is producing? Avalanche region is producing. Across P to
P to N is drift.
Drift region is produced. This explanation you have to give you. Next, come to the trap-at diode. In trap-at diode, the drift concept is not given. Which combination is taken? P plus and N plus is taken. P plus and N plus is taken. Just observe the difference. P plus and N plus is taken. This one we have to Sir, mute చేసేసారా స్టూడెంట్స్ ని? Now we are discussing which diode? Trap-at diode. Trap-at diode is a combination of P plus and N plus. To this one, we have to explain the graph in the examination. What we have graph? Like this you have. Initially, like this. Again, this you have. Again, this one you have. Again, this one. Explanation of the graph you have to do in the examination. For which one? Trap-at diode. Now we are discussing the topic is trap-at diode. Trap-at diode is a combination of P plus and N plus. Here, initially the current is increased. The capacitor is charged. The diode acts as a capacitor and it is charging. Up to what point it will? From A to B, it is charging. From A to B, it is charging. P to C, C to D, it is discharging. Again, D to E, it is increasing. Again, from E to C point. From A to B increasing, from B to D decreasing, D to E again increasing, up to G point it is increasing, again this is decreasing. So this answer you have to explain the combination what we are writing, why it is increasing, why it is decreasing, again why it is slowly increasing here. Now here first the diode is conducting. The diode is conducting in forward bias, it is increasing. If the diode conducts, what happens? Recombination of electrons and holes takes place. Recombination between these two is taking place. If recombination is taking place, one hole and one electron is combined. What happens? It will generate two holes and two electrons. As combination, the child is produced here. So one electron, one hole combined means more electron hole pairs are generated. If more electron hole pairs are generated, some plasma is formed in this region. Why? What is the term I am calling plasma is generating? Plasma is generating means more number of electron hole pairs are produced. If more number of electron holes are produced, it is decreasing. Decreasing means plasma is formed. Again, what we are doing after plasma is formed, we are removed plasma across D. Removing of plasma across D. From D to E, plasma is removed. If plasma is removed from E to G, again the current is increasing. Again, it is constant. Again, I am repeating, you have to explain the graph here. What is the graph? When the diode is in forward bias condition, recombination of holes and electron pair takes place. When recombination is going on, it is first current is like this, it is increased. Recombination of electrons and holes are taking place. After this recombination of electrons and hole pair space, suppose here 2 electrons, 2 holes. How much it is? 4. By combining with another 4, it is producing 8. By combining again, it is producing few more 8. So number of electron and hole pairs are increasing in quantity. If it is increasing in quantity, some region is formed across the diode. That region is called as plasma region. When plasma region is formed, immediately what happening? This current is decreasing. This current is decreasing. So what we are doing, that plasma is removed. From which point to which point plasma is removed? From this point to here, the plasma is removed. After plasma removed, again the current is increasing. Again, it is constant. Now this one we have to give explanation. From point A to point B, what happening, ma'am? It is forward biased, increased. Electron hole recombination is taking place. From B to C, what happens? Some region is formed as electron hole pair produced more. For that, current is decreased. From C to D, what we are doing? Whatever the region is formed, we are removing that region. So, this much time period, space it is taking to remove. After removing complete plasma, again it is increasing. Again it is constant. Now we will see this one in the PPT. See here. From here, the topic will start. Either you can take P plus N, N plus combination or N plus P, P plus combination. Don't get confusion, ma. This one is in the textbook. This part is given in the page number 82 and it is mentioned in impact diode. This 82 page explanation you have to write for trapad diode. Trapad diode. So we can take P plus P N combination, P plus N N combination. This is the first one. When potential energy is applying or some voltage is applying is given here. And next, see this diagram is very important. What happening from A to B? The
Ma'am,
diode
share
is
your
charging.
PPT, no?
The diode is charging. From A to B, the diode is charging. From B to C, what happening? Plasma is
Region
formed.
is formed.
From
Region is formed.
some plasma region is forming. As
Formed.
plasma region is forming, what happened to the voltage here? Voltage is decreasing. From which point to which point the voltage is decreased?
to D.
From C to D,
C
the
to D.
voltage is decreased. Again, from D to G, what we are doing is mentioned with different points. B to C is what happened? Plasma formation. What is happening from C to D? Completely plasma voltage is fall down. From D to G, voltage is increased. Across the point G, again the diode is charging. What happening across the point F? What is happening across the point E? From D to E, what happening, ma? Extraction of plasma. Plasma is removed. What is happening from E to F? Maybe at the corners some plasma is present. We are removing the plasma across the corners. From where? E to F. From F to G, what happened? Complete plasma is removed. After completely plasma is removed, again the diode is charged and increased and it is constant. This one is explained in point wise. Just here, what happening across point A? What happening across
Ma'am,
point A? The
ma'am.
diode is conducting. చెప్పండమ్మా.
If you have a PPT, then share us, na?
I will share the PPT.
Okay.
What happened to the point A? Point A, what happening? The
It's not-
diode is conducting, current is
Conducting.
increasing. One first
Yes.
point. From A to B, what happening? From A to B, current is
Forward
increasing.
bias.
From B to C, what
Forward bias.
happening? More electron hole
Current
pairs
is
are
decreases.
generated. More electron hole pairs are generated. Plasma is formed. As plasma is formed, voltage is dropped from C to D. From C to D, voltage is dropped. Across D to E, what happening? Plasma is extraction. The plasma extraction in the middle, not at the edges. Again, we are cross-checking at the edges from the point E to F. Residual extraction is anything is there at the ends. We are cross-checking. After cross-checking, again the diode is increased. Up to what extent it is increasing? Up to diode G point, it is increasing. Again, the voltage is constant and it is increased. So, this is explained with these slides. What is the point A? Diode is conducting, current is increasing. Across, again, due to some thermal agitation, each point
Excuse me,
is
ma'am, are you showing PPT?
Yes.
But we are unable to see.
Yes, ma'am. We are.
Could you please share your screen? Yeah, now we can see, ma'am.
Is this slide okay, ma?
Yes, ma'am.
Yes, ma'am.
Now okay.
Now,
There in textbook, no, ma'am.
yeah, everything is in the textbook, ma. Everything is in the textbook. Based on the textbook only. Please mute
But all
yourself.
of them are not having textbook, ma'am, right now. So if you show PPT, that will be helpful for us.
Okay, okay. Mute yourself, ma.
ఐదు వస్తలేమా ఈ రోజే ఫస్ట్ వచ్చింది
Tapad diode, its introduction. Next, how it is charging, discharging, and explanation part. This one you have to give in the Tapad diode. Next, what we discussed before Tapad diode, what we discussed, another diode we discussed is impact diode. What is impact diode? Impact, ionization, avalanche, transition time. Here, this functioning we have to write, and how the voltage characteristics, and what about the electric field, how electric field is varying, how doping position is taking place. This is impact diode. Next, first what we discussed today. First we will discuss today is, which one we discussed first today is tunnel diode and its application. 3 questions. Out of these 3 questions, you will get one important essay question. What is the first question we discussed? Tunnel diode, impact diode, trapper diode. You learn these questions from this chapter. Tunnel diode symbol, introduction, its applications is given in the first slide. In the second slide, it is given by applying voltage. In the textbook diagram, C, D, E, F is only mentioned, how the energy levels is varying, and what happens if we are applying load. Up to here, one essay question. Next essay question is application. If we connect this one in serial, what happens? If we connect this one in the parallel, what happens? For this, we are calculating gain. Gain calculation we already did in the beginning now. Where is gain calculation? What is the gain formula, ma? What is the gain formula? Gain equal to minus di by dv times of Vn, where I is the current and V is the voltage. Here, why we are taking negative symbol? Negative symbol we are taking because of negative conductance point. To this one, I am connecting load across serial and across parallel. Now, I am starting next unit in this only parametric amplifier, unit 9. This parametric amplifier, we will get short question. I will cover parametric amplifier and I will stop in 15 minutes. Next topic is parametric amplifier, page number 89. Parametric amplifier, page number 89. In this parametric amplifier, we are connecting one ideal circuit, one signal circuit, another one is pump circuit. Here we have three circuits. How to learn the diagram for the examination point of view? We have one resistor, one inductor, one capacitor. This is which part? Signal part. For this signal part, I am representing with RS, inductor RL, capacitor is C. This is signal circuit. To the signal circuit, this is inductor is represented with L. Inductor is represented with L. So resistance R, inductor L, capacitor, signal source side. Same we have ideal circuit. Ideal circuit, again I have one capacitor, again one inductor, again one resistor. Resistor is RL, inductor is LL, capacitor is CL. To this one, I am connecting another circuit. What is another circuit? Pump circuit. Which combination? Pump circuit RP. What is the inductor we will call? Inductor is LP. What is the capacitor we will call? CP. This combination is joining to this point. To this, I am connecting one variable common capacitor CT varying with respect to time. CT. Variable capacitor varying with respect to time. To all these terminals, I am connecting one signal source. To all these terminals, I am connecting one signal source. This is the diagram of parametric amplifier. From this chapter, 5 marks important questions. Maybe you will get previous years, as I'm just saying, as per the previous year questions. This is parametric amplifier. So how to draw the diagram? It is the combination of three. One is signal circuit, another one is ideal circuit, another one is pump circuit. This part represents signal circuit. This part represents ideal circuit. This part represents what? Pump circuit. Using this, we are doing derivation part. What is the derivation is given here? Using this, we are taking two frequencies. One frequency is signal frequency I am represented with S. Next, another frequency is pump circuit frequency I am representing with F. So, these two frequencies is taking as a sum of the frequency as well as difference of the frequency. If the sum of the frequency is represented with Fs plus Fp, difference of the frequency is represented with Fs minus Fp. Using this, I am writing formulas output frequency F0. What is output frequency F0? F0 equal to sum and differences of frequencies. F0 equal to Fs plus Fp or else Fs minus Fv. To this, I am using M. What is M here? M is the modulating circuit we will call. M and N are two positive integers. Here, M and N are two positive integers. M times of Fs, N times of Fp. Using this, I am writing output frequency. Using this, I am writing output frequency F0. What is F0? F0 equal to two integers, M times of signal frequency Fs plus or minus N times of signal frequency Fp. Here, we have to cross check that if output frequency F0 is greater than signal frequency, if output frequency F0 is lesser than signal frequency. If output frequency is greater than signal frequency, we will call this as what we will call parametric up counter. If the output frequency F0 is lesser than signal frequency, we will call as parametric down counter. Parametric up counter and parametric down counter. This parametric up counter and down counter, we have derivation part, small two lines derivation we have. What is first we will see up counter. Up counter means we will take positive, down counter means we will take negative. F0 what we have? F0 equal to Fs plus Fp. From this, what we have to write? We have to write the gain formula. Direct we have formula. What is the gain formula? Gain equal to F0 by Fs is given as F0 Fs into S by under root of 1 plus x square. We have already this one in the direct formula notation. You write F. F naught by Fs is equal to x by under root of what is the formula of up counter? F naught by Fs times of into x x by 1 plus under root of 1 plus x square. 1 plus x whole square. Direct formula we have. This is for up counter. Same way we have formula for down counter also. What is the difference between up counter and down counter? In up.
Excuse ma'am, there is no
Not
root, ma'am.
a counter, madam. That's a converter. Converter.
Converter. What I said?
Ma'am, excuse ma'am,
Amma,
there is no root.
what Amma?
Excuse ma'am,
Yes.
there is no root in the formula. Gainer.
For the denominator, we have formula, no? Root of 1 plus x. What? F naught times of Fs. X by 1 plus under root of 1 plus x. Cross check this one.
Yes, ma'am.
Whole square. If it is up, if it is down, what is the difference between the up and down? For down, you have Fs by F naught. For down, you have Fs by F naught. Using this, we are calculating quality factor Q. Quality factor Q equal to 1 by 2 pi Fs C times of Rd. Direct, you can, so here we are representing direct formulas. So this is up converter and down converter, parametric amplifier we have. This parametric amplifier is 5 marks question from this chapter. Another topic is there in this essay question. Manly power relation. I will cover this derivation part tomorrow.
Okay,
Any
ma'am.
doubts? Any doubts in the today's class, ma?
मैडम पीपीटी कवाली
You ask about doubts, not about PPT. Subject to doubts. I will share PPT in the group, okay?
మ్యామ్ ఒకసారి డయాగ్రామ్ లో సంగీత మ్యామ్ మార్నింగ్
చెప్పండి. Good morning.
ఇది డయాగ్రామ్ లో 3 పార్ట్స్ చెప్పారు కదా ఎఫ్ఎస్ ఇప్పుడు మనకి సర్క్యూట్ డయాగ్రామ్ లో మేడం పారామెట్రిక్ యాంప్లిఫైర్ లో ఇప్పుడుదే మేడం
పారామెట్రిక్ యాంప్లిఫైర్ ఓకే అమ్మా
దాంట్లో టెక్స్ట్ బుక్ లో డయాగ్రామ్ ఉంది మీరు చెప్పింది సో ఏది ఎఫ్ఎస్ ఏది ఎఫ్పి కొంచెం ఒక్కసారి మళ్ళీ చెప్పరా మేడం అది
ఓకే ఫస్ట్ పార్ట్ ఏమో సిగ్నల్ సర్క్యూట్ మేడం ఆర్ఎస్ ఎల్ఎస్ సిఎస్ 3 కవర్ అయ్యాయి చూడండి ఆర్ఎస్ ఎల్ఎస్ సిఎస్
ఎస్ మేడం
అది సిగ్నల్ పార్ట్ ఐడియల్ పార్ట్ లోనేమో సిఎల్ ఎల్ఎల్ ఆర్ఎల్
ఐడియల్ పార్ట్ లో సిఎస్
సిఎల్ ఎల్ఎల్ ఆర్ఎల్
ఓకే సిఎల్
ఎల్ఎల్
ఆర్ఎల్ ఓకే
నెక్స్ట్ పంప్ పార్ట్ లో ఆర్పి ఎల్పి సిపి
ఆర్పి ఎల్పి సి
to these we are connecting signal voltage Vs.
Okay.
And in the middle, variable capacitors. Just observe the diagram. In parametric amplifier, the capacitor we have arrow symbol.
Okay.
That is variable, varying with respect to the time. And two frequencies we have FP plus Fs. Up is plus, down is minus. According to that, we are writing gain formula and quality factor, two formulas.
ఓకే సో ఇది ఇక్కడ వరకే స్టాప్ మేడం ఎఫ్ గెయిన్ ఈజ్ ఈక్వల్స్ టు ఎఫ్ నాట్ బై ఎఫ్ ఎస్ ఇంటూ 1 ప్లస్ అండర్ రూట్ 1 ప్లస్ ఎక్స్ హోల్ స్క్వేర్ ఇది ఇక్కడ వరకు
అక్కడ వరకు రాసేసి మనకి ఇక్కడ డైరెక్ట్ ఫార్ములా మెన్షన్ చేస్తారు మేడం క్వాలిటీ ఫ్యాక్టర్ ది
ఓకే
ఒక ఫార్ములాస్ రెండు రాసేసేయండి అంతే దానికి నెక్స్ట్ పేజ్ లో ఎఫ్ ది రాయకుండా ఓకే బ్యాండ్ విడ్త్ ఫార్ములా ఒకటి మెన్షన్ చేయండి
Okay. Ma'am, this question is for 5 marks actually.
5 marks short question.
Okay, ma'am.
Parameter
If we If we
amplifier.
write, if we draw this diagram and till gain formula, is that okay, ma'am?
No. You have to write down part also. For up and down converter, both gain formulas as well as up to quality factor Q you have to mention.
Up to page number 90, ma'am.
Up to page number 90.
Parametric down converter.
Down converter.
Up to there, ma'am.
Yes.
Okay, ma'am. Thank you, ma'am.
And in the essay questions, you have to learn 3. What are the 3 essay questions you have? Negative
Which we discussed today.
tunnel diode.
Yes.
In tunnel diode, it is very important to explain A, B, C, D, E, F diagrams. You will get question characteristics.
VI characteristics,
VI characteristics అంటే 8.1 లో ABCDEF పేజ్ నెంబర్ 76 లో డయాగ్రామ్స్ వేయాలి. PPT లో ఉంది. వేసేసి గ్రాఫ్ ఎక్స్ప్లెయిన్ చేయాలి. Why it is increasing, why it is decreasing. This graph you have to correlate with this energy, Fermi energy level diagrams.
Okay, madam.
Ma'am, it includes series loading as well.
Series parallel load is another question.
Yes, Omera.
Okay, ma'am. Okay, ma'am. I understood, ma'am.
Up to characteristic one topic. Tunnel diode as microwave amplifier is another topic.
The application
One more is impact diode.
చెప్పండి మేడం.
అప్లికేషన్ ఆఫ్ టన్నల్ డయోడ్ లో యాంప్లిఫైయర్ వస్తుంది కదా మేడం.
యాంప్లిఫైయర్ వేయాలి. సీరియల్ ప్యారలల్ లోడింగ్ డయాగ్రామ్స్ వేసి ఒక చిన్న డెరివేషన్ పార్ట్ ఉంది, అది రాసేసేయండి మేడం ఇక్కడ.
ఓకే మేడం.
దట్స్ ఇట్. అండ్ సెకండ్ టాపిక్ లోనేమో ఇంపాక్ట్ డయోడ్ లోనేమో వోల్టేజ్ కరెంట్ 81 పేజ్ ఉంది కదా మేడం.
ఎస్ మ్యామ్.
81 పేజ్ వరకు రాయాలి. 82 పేజ్ ది మాత్రం ట్రాపాడ్ డయోడ్ లో రాయండి.
అది బిఫోర్ ఏ డయాగ్రామ్ ఇచ్చిండు కదా మేడం.
డయాగ్రామ్ ఇచ్చి ఇల్లు ఎక్స్ప్లెయిన్ చేసారు.
కానీ ఇక్కడ టాపిక్ ఏమో ఇక్కడ స్టార్ట్ అయింది, డయాగ్రామ్ ఏమో లెఫ్ట్ సైడ్ ఉంది. మీరు PPT లో కూడా పెట్టారు కదా.
పెట్టాను. ఐ విల్ షేర్ దట్ వన్. నెక్స్ట్ షార్ట్ క్వశ్చన్ ఏమో పారామెట్రిక్ యాంప్లిఫైర్. టుమారో క్లాస్ ఐ విల్ డిస్కస్ Manley row power relation ఒకటి ఉంది. Or else I will start.
This is a long answer, ma'am. Manley row power relations.
I will cross check with the previous papers. I didn't check.
Okay, sure.
Okay, ma'am. Class completed.
మేడం 1 minute మ్యామ్. ఇప్పుడు మళ్ళీ 1 o'clock 1:30 కూడా క్లాస్ మీదేనా మేడం?
లేదమ్మా, నాది కాదు.
ఓకే, థ్యాంక్ యూ.